Welcome to this explainer. Imagine the exact moment of first contact. It probably isn't going to be a giant dramatic spaceship hovering over a major city, right? Actually, it's way more likely to be a subtle, mathematical anomaly buried deep inside petabytes of raw radio data. Today, we're diving into how machine learning is actively powering this exact first contact scenario. For all you astrophysics students and data nerds out there, we're going to get right into the mathematical rigor behind this. We'll explore how deep neural networks are being deployed to filter out cosmic background noise and isolate potential non-random patterns from the stars.
So let's start with a basic question. What exactly constitutes a sign of non-human intelligence? Structurally speaking, we aren't just looking for really loud energy spikes. We're searching for highly specific mathematical signatures. Think extremely narrowband signals, distinct amplitude modulations, or non-random periodicities that known astrophysical phenomena just don't produce. The core challenge here is recognizing a structured, artificial pattern that we've literally never encountered before. It's essentially finding a mathematical needle in a galactic haystack. Okay, let's dive right into section 1, the cosmic noise mystery. Because before we can even search for intelligence, we really need to deeply understand the chaotic environment we're listening to. So how do we isolate one fragile artificial signal from the absolute deafening roar of the galaxy? Well, the very first step is aggressive radio frequency interference, or RFI mitigation. Think about your everyday noise-canceling headphones. They use tiny microphones to detect ambient sound and then generate a phase-inverted wave to cancel it out, right? We apply a conceptually similar but mathematically massive approach to cosmic data using tensor calculus and high-resolution spectrograms. We literally have to mathematically model and strip away the background radiation, the interference from our own Earth satellites, and the natural broadband emissions of billions of stars. It is a huge task. Now, what happens when an algorithm actually flags an anomaly in this cleaned-up data? This is where deep learning models step in, to identify unusual astrophysical structures. But I have to be honest, the risk of false positives here is exceptionally high. A highly regular signal might look totally artificial at first glance, but mathematically, it could easily just be a rapidly spinning pulsar, or maybe the complex electromagnetic emissions of a distant quasar. Because of this, convolutional neural networks are trained on massive datasets of known natural phenomena. That way they can accurately assign probability scores, separating the naturally fascinating stuff from the genuinely artificial. Moving right along to section 2, AI as a translator. To actually process all of this galactic chaos at scale, we have to turn to artificial intelligence. You might be wondering, how exactly do these algorithms interpret this massive amount of data? Well, we use advanced neural network architectures that are pretty similar to the natural language processing, or NLP, models that translate earthly languages. But instead of mapping French syntax to English, these sequence-to-sequence algorithms are mapping the raw, multi-channel static of the universe into high-dimensional feature spaces. They're analyzing topological data to find hidden syntactic structures within the radio waves themselves. Basically, they're looking for mathematical grammar where standard algorithms just see pure static. Are there concrete examples of this working in the real world? Absolutely, yes. Just look at the recent breakthroughs in detecting fast radio bursts, or FRBs. For years, traditional algorithms completely missed faint, repeating FRBs because the signals were buried under massive dispersion measures. But when researchers finally applied machine learning, the algorithms successfully detected the complex hidden periodicities and nonlinear patterns that standard linear searches just completely overlooked. The AI literally parsed the noise and found the underlying structure. It's a real game changer. But here's a really important question. How do we prevent our own human-centric training data from skewing the results? This is a massive interpretational bias and an ethical hurdle that we absolutely must solve. When we train AI, we risk injecting anthropocentrism, basically teaching it what we think communication looks like. Out in deep space, a non-human intelligence will probably use mathematical frameworks or communication protocols completely alien to human logic. To counter this, algorithms are increasingly being designed for unsupervised learning. This means they cluster data organically rather than forcing cosmic signals into predefined human-centric boxes. Which brings us to section 3, searching for extraterrestrial life. Let's put the problem and the tool together. So where does this technology take us over the next decade? Well, we are entering an era of exponential data processing. As next-generation arrays like the massive square-kilometer array come online, the influx of data is going to be completely unprecedented. Coupling these huge radio telescopes with unsupervised machine learning means our capacity to sift through the cosmos will increase by orders of magnitude. We are fundamentally shifting from just passively listening to the algorithmic, high-throughput verification of deep space anomalies. So, will advanced neural networks be the key that finally unlocks the cosmic static? We are standing on a profound mathematical and existential threshold right now. The transition from raw, chaotic telemetry to algorithmically verified intelligence isn't science fiction anymore. It is an active, highly rigorous scientific pursuit. The first undeniable evidence of extraterrestrial intelligence might literally already be captured in our data archives right now, quietly waiting for the exact right algorithm to reveal it.